In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about vacuum drying. Vacuum drying is the mass transfer operation in which the moisture present in a substance, usually a wet solid, is removed by means of creating a vacuum. In chemical processing industries like food processing, pharmacology, agriculture, and textile, drying is an essential unit operation to remove moisture. Vacuum drying is generally used for the drying of substances that are hygroscopic and heat sensitive, and is based on the principle of creating a vacuum to decrease the chamber pressure below the vapor pressure of the water, causing it to boil. With the help of vacuum pumps, the pressure is reduced around the substance to be dried. This decreases the boiling point of water inside that product and thereby increases the rate of evaporating significantly. The result is a significantly increased drying rate of the product. The vacuum drying process is a batch operation performed at reduced pressure and lower relative humidity compared to ambient pressure, enabling faster drying. And the next part is a vacuum dryer. Vacuum dryer is the equipment with the help of which vacuum drying is carried out. Vacuum dryers are sometimes made up of cast iron, but most are made of stainless steel so that they can bear the high vacuum pressure without any kind of deformation. The oven is divided into hollow trays, which increases the surface area for heat conduction. The oven door is locked airtight and is connected to a vacuum pump to reduce the pressure. The materials to be dried are kept on the trays inside the vacuum dryer, and pressure is reduced by means of a vacuum pump. The dryer door is tightly shut and steam is passed through the space between trays and jackets so that the heat transfer happens by conduction. Water vapors from the feed is sent into the condenser, and after the drying, vacuum pump is disconnected and the dried product is collected from the trays. The next part is microwave vacuum drying. Because conventional drying approaches, for example convective drying, may cause great nutritional and textural changes like a darker color due to Maillard reaction, microwave vacuum drying is an alternative for pharmacology and food drying, a method now since 1981. The microwaves speed up the drying process and lower temperature in vacuum system, reducing overall drying cycle time and temperature induced effect of the food product. Non-primarily source and microwave vacuum drying may be used for production of dried pharmacology and food. Industrialized equipment, however, may require pre-treating samples before processing. In industrial vacuum system, pre-drying is used by conventional methods to reduce bulk water content. And what are the applications? A vacuum dryer can be used to dry heat-sensitive hygroscopic and toxic material. If the feed for drying is a solution, it can be dried using vacuum dryer as the solvent can be recovered by condensation. To improve the quality of products such as for fruit preservation, hybrid drying combination osmotic dehydration followed by heat pump drying and microwave vacuum drying proved effective. And what about the mass transfer? Mass transfer is the net movement of mass from one location, usually meaning stream, phase, fraction, or component to another. Mass transfer happens in many processes such as absorption, evaporation, drying, precipitation, membrane filtration, and distillation. Mass transfer is used by different scientific disciplines for different processes and mechanisms. The phrase is commonly used in engineering for physical processes that involve the diffusive and convective transport of chemical species within physical systems. Some common examples of mass transfer processes are the evaporation of water from a pond to the atmosphere, the purification of blood in the kidney and liver, and the distillation of alcohol. In industrial processes, mass transfer operations include separation of chemical components in distillation columns, absorbs such as scrubbers or stripping adsorbers such as activated carbon beds and liquid extraction. Mass transfer is often coupled to additional transport processes, for instance, in industrial cooling towers. These towers couple heat transfer to mass transfer by allowing hot water to flow in contact with air. The water is cooled by expelling some of its content in the form of water vapor. And what about the astrophysics? In astrophysics, mass transfer is the process by which matter gravitationally bound to a body. Usually, a star fills its Roche lobe and becomes gravitationally bound to a second body, usually compact object, white dwarf, neutron star, or black hole, and is eventually accreted onto it. It is a common phenomenon in binary systems and may play an important role in some types of supernova and pulsars. And what about the chemical engineering? Mass transfer finds extensive application in chemical engineering problems. It is used in reaction engineering, separations engineering, heat transfer engineering, and many other subdisciplines of chemical engineering like electrochemical engineering. The driving force for mass transfer is usually difference in chemical potential when it can be defined how other thermodynamic gradients may couple to the flow of mass and drive it as well. A chemical species moves from areas of high chemical potential to areas of low chemical potential. Thus, the maximum theoretical extent of a given mass transfer is typically determined by the point at which the chemical potential is uniform. For single-phase systems, this usually translates to uniform concentration throughout the phase, while for multi-phase systems, chemical species will often prefer one phase over the others and reach a uniform chemical potential only when most of the chemical species has been absorbed into the preferred phase, as in liquid extraction. While thermodynamic equilibrium determines the theoretical extent of a given mass transfer operation, the actual rate of mass transfer will depend on additional factors including the flow patterns within the system and the diffusivity of the species in each phase. This rate can be quantified through the calculation and application of mass transfer coefficients for an overall process. These mass transfer coefficients are typically published in terms of dimensionless numbers, often including Peclet number, Reynolds number, Sherwood number, and Schmidt numbers, among others. And what about the analogies between heat, mass, and momentum transfer? Transport phenomena, and there are notable similarities in the commonly used approximate differential equation for momentum, heat, and mass transfer. The molecular transfer equations of Newton's law for fluid momentum and law Reynolds number, Stokes flow, Fourier's law for heat, and Fick's law for mass are very similar, since they are all linear approximations to transport of conserved quantities in a fluid field. At high Reynolds number, the analogy between mass and heat transfer and momentum transfer becomes less useful due to nonlinearity of the Navier-Stokes equation, or more fundamentally, the general momentum conservation equation. But the analogy between heat and mass transfer remains good. A great deal of effort has been devoted to developing analogies among these three transport processes so as to allow prediction of one from any of the others. And what about the vacuum? A vacuum is a space devoid of matter. The word is derived from the Latin adjective vacuus or neutral vacuum, meaning vacant or void. An approximation to such vacuum is a region with a gaseous pressure much less than atmospheric pressure. Physicists often discuss ideal test results that would happen in a perfect vacuum, which they sometimes simply call vacuum or free space, and use the term partial vacuum to refer to an actual imperfect vacuum as one might have in a laboratory or in a space. In engineering and applied physics, on the other hand, vacuum refers to any space in which the pressure is considerably lower than atmospheric pressure. The Latin term in vacuum is used to describe an object that is surrounded by a vacuum. The quality of a partial vacuum refers to how closely it approaches a perfect vacuum. Other things equal lower gas pressure means higher quality vacuum. For example, a typical vacuum cleaner produces enough suction to reduce air pressure by around 20%. But higher quality vacuums are possible. Ultra high vacuum chambers, common in chemistry, physics, and engineering, operate below 1 trillion net, between 10 to 12 of atmospheric pressure, and which is about 100 pascal, and can reach around 100 particles per centimeter cubic. Outer space is an even higher quality vacuum with the equivalent of just a few hydrogen atoms per cubic meter on average in intergalactic space. Vacuum has been a frequent topic of philosophical debate since ancient Greek times, but was not studied empirically until the 17th century. Solomon's Templar, 1609, philosophized about the experimental possibility of producing a vacuum in small tubes. Evangelista Torricelli produced the first laboratory vacuum in 1643, and other experimental techniques were developed as a result of his theories of atmospheric pressure. To Torricellian, vacuum is created by filling with mercury a tall glass container closed at one end and then inverting it in a bowl to contain the mercury. Vacuum became a valuable industrial tool in the 20th century with the introduction of incandescent light bulbs and vacuum tubes, and a wide array of vacuum technologies has since become available. The development of human spaceflight has raised interest in the impact of vacuum on human health and life forms in general. And what about the etymology? The word vacuum comes from Latin and empty space, void, and non-use of neuter of vacuous, meaning empty, related to vacare, meaning to be empty. Vacuum is one of the few words in the English language that contains two consecutive instances of the vowel. And what about the historical understanding? Historically, there has been much dispute over whether such a thing as a vacuum can exist. Ancient Greek philosophers debated the existence of a vacuum or void in the context of atomism, which posited void and atom as the fundamental explanatory element of physics. Lucretius argued for the existence of vacuum in the first century before Christian, and Hero of Alexandrian tried unsuccessfully to create an artificial vacuum in the first century after AD. Following Plato, however, even the abstract concept of a featureless void faced considerable skepticism. It could not be apprehended by the senses. It could not itself provide additional explanatory power beyond the physical volume which it was commensurate, and by definition it was quite literally nothing at all, which cannot rightly be said to exist. Aristotle believed that no void could happen naturally because the denser surrounding material continuum would immediately fill any incipient rarity that might give rise to a void. In his physics book, Aristotle offered numerous arguments against the void. For example, that motion through a medium which offered no impediment could continue ad infinitum. There being no reason that sometimes would come to rest anywhere, in particular in the medieval Muslim world, the physicist and the Islamist scholar Al-Farabi wrote a treatise rejecting the existence of the vacuum in the 10th century. He concluded that air's volume can expanded to fill available space, and therefore the concept of a perfect vacuum was incoherent. According to Dalal and Royhan, states that there is no observable evidence that rules out the possibility of vacuum. The suction pump was described by Arab engineer Jazari in the 13th century and later appeared in Europe from the 15th century. European scholars such as Roger Bacon, Blasius of Parma, and Walter Bruley in the 13th and 14th century focused considerable attention on issues concerning the concept of a vacuum. The commonly held view that nature abhorred a vacuum was called horror vacuum. There was even a speculation that even God could not create a vacuum if he wanted, and the 1277 Paris condemnation of Bishop Etienne Tampier, which required there to be no restrictions on the powers of God, led to the conclusion that God could create a vacuum if he so wished. From the 14th century onward, increasingly departed from the Aristotelian perspective, scholars widely acknowledge that a supernatural void exists beyond the confines of the cosmos itself by the 17th century. This idea influenced the Stoic physics, helped to segregate natural and theological concepts. Almost 2,000 years after Plato and Descartes also proposed a geometrically based alternative theory of atomism, without the problematic noting everything dichotomy of void and atom. Although these researchers agreed with the contemporary position that a vacuum doesn't happen in nature, the success of his namesake coordinate system, and more implicitly the special corporeal component of his metaphysics, would come to define the philosophically modern notion of empty space as a quantified extension of volume. By the ancient definition, however, directional information and magnitude were conceptually distinct. Medieval thought experiments into the idea of vacuum considered whether a vacuum was present, if only for an instant, between two flat plates when they were rapidly separated. There was much discussion of whether the air moved in quickly enough as the plates were separated, or as Walter Bruley postulated, whether a celestial agent prevented the vacuum arising. And another researcher, Buridian, reported in 14th century that teams of 10 horses could not pull open blues when the port was sealed. The 17th century saw the first attempts to quantify measurements of partial vacuum. Evangelista Torricelli's mercury barometer of 1643 and Blaise Pascal's experiments both demonstrated a partial vacuum. In 1654, Otto von Guericke invented the first vacuum pump and conducted his famous Magdeburg hemispheres experiment, showing that owing to atmospheric pressure outside the hemispheres, teams of horses could not separate two hemispheres from which the air had been partially evacuated. Robert Boyle improved Gurik's design, and with the help of Robert Hooke further developed vacuum pump technology. Thereafter, research into the partial vacuum lapsed until 1850, when August Toepler even invented the Toepler pump, and 1855, when Heinrich Geissler invented the mercury displacement pump, achieving a partial vacuum of about 10 Pascal, which is equal to zero point 0.1 torr. A number of electrical properties become observable at this vacuum level, which renewed interest in further research. While outer space provides the most rarefied example of a naturally happening partial vacuum, the heavens were originally thought to be seamlessly filled by a rigid indestructible material called ether. Borrowing somewhat from the phenomena of Stoic physics, ether came to be regarded as the rarefied air from which it took its name. Early theories of light posited a ubiquitous terrestrial and celestial medium through which light propagated. Additionally, the concept informed Isaac Newton's explanations of both refraction and radiant heat. 19th century experiments into this luminiferous ether attempt to detect a minute drag on the Earth's orbit, while the Earth does, in fact, move through a relatively dense medium in comparison to that of interstellar space, and the drag is so harsh that it could not be detected. In 1912, astronomer Henry Pickering commented, while the interstellar absorbing medium may be simply the ether, its characteristics of gas and free gases molecules are certainly there. Thereafter, however, luminiferous ether was discarded, and later in 1930, Paul Dirac proposed a model of a vacuum as an infinite sea of particles possessing negative energy, called the Dirac sea, and the theory helped refine the prediction of his earlier formulator. And the comparison to that interstellar space, the drag is so minor that it could not be detected. And now in the capsule simulation, you can see that for creating this vacuum in the component, we have a circular and circular here. And the material we have used is a multi-phase material because we want to pass through a two-phase, solid phase, and also vacuum phase. In order to we can depict our simulation, I have used heat transfer in solid and also coefficient form of PDE for a vacuum because we have a dimensionless, and there is an equation here, and also we have a parameters to define the values for either for geometry or for physics parameters that we have used in the later equation. You can see that a specific heat capacity for gas, liquid, solid, and different things, and latent heat of vaporization, and the diffusion coefficient, evaporation rate constant, and molar mass and density, residual saturation, and etc. And here for the you can see the temperature, coefficient form, and they are for PDE that you can see a semicircle and evaporation rate. Thank you so much for watching my video until the end, and also you can download this video from github.com/masterscript.